Right. So there's your heading. Now, before we put any pen to paper, I've sort of mentioned this last couple of lessons, but let me say it again, okay? Some of you have already met or heard about or read about integration and integrals, okay? Now, I just want to do a quick survey. Hands up who has, even if you have no understanding of what it is, hands up if you've heard of those terms before. Yeah? Okay, all right, now keep your hand up if you actually know something about them, like how to get one, what they refer to, that kind of thing. Hands straight up so I can see. That's okay. All right, thank you. Hands down. Now, I assume a lot of you will have, okay? And I think at this point in the course I had as well. Now, let me try and explain why I'm not going to talk about integration at all until next term. Apart from the whole fact that, Board of Studies says I ought not to, okay? Because you guys are still primitive students. Primitives and integrals, okay? A lot of people, at least the people who had their hands up just now, who know a bit about these, might feel like these are really similar to each other, okay, which is kind of right. You might think they're the same, okay? You might have even been taught they're the same thing, okay? Now here's the thing. If you feel like they're the same thing, this is a failure of the education you have received, or the teacher who taught you that they're the same, okay? Because in fact, it's one of the biggest mysteries in maths, right? That these two things actually have anything to do with each other, okay? So sort of, if you ever, sat down in class, or you read something, or you watched something, and they taught you, okay, there's this thing, and there's this thing, and they're much the same. It's a little bit like, in a movie where there's like, there's a good guy and a bad guy, but the bad guy, you only find out he's the bad guy at like very, very close to the end, right? It's kind of like a big reveal and everyone's like, what? No? Are you serious? It's kind of like sorry, I'm going to spoil something. It's kind of like Snape, right? So, spoilers, so Snape, well, tough, okay? It's too many years in advance. So Snape's a good guy, right? But the whole way through the series, everyone's like,
it's the opposite.
Oh, really? And when you finally get the reveal, right? And everything clicks, you're like, really? That's who he is? That's his identity? Come on, grab a sheet. Okay. And then you have to go back and rewatch everything. You're like, oh, my mind's, exploding, okay? Now imagine if in the very first book, okay, the very first movie, whichever you watched, okay, they're like, oh yeah, by the way, he's a good guy. Actually, he's like, the whole story like turns on him. Maybe someone did this to you. It kind of, like, the story is still okay, but it spoils much of the drama and what makes it interesting, right? So, there's a big mathematical journey that we have to go on to try and show the connection between these two, okay? So I'm going to deal with these, and we'll deal with these, I'll introduce them properly next term. If you feel like these are the same, I need you to try and unlearn some of that, okay? So that we can give this topic its proper introduction. Okay, does that make sense? Yeah? All right. So now that I've told you I'm not going to talk about this, let me put it up. Okay. Now, primitives. What does it mean? Primitive is, well, when you say the word primitive in English, what does it usually conjure up images of? I actually would think usually Justin, but anyway, Neanderthals, Cro-Magnon man, that kind of thing. So primitive tends to mean old, right? It's like where things came from. Okay. So we're using it as kind of an opposite to the word derivative. Okay, primitive, derivative. Derivative is when you take something, you don't derive it, you differentiate it, right? It undergoes some process, and then this is what you end up with. Okay, so primitive is like answering the question, well, okay, where did the derivative come from, right? Does that make sense? So differentiating.
So you have a derivative and you figure out the
Yeah, okay, so if you have some kind of function, okay, for example, x squared, okay, when you differentiate it, you get the derivative, okay, so that's differentiating, that's an example, right? Now, the opposite process, mark this, okay, because it's the opposite of differentiation, its proper name is anti-differentiation. You're trying to undo. Okay. Okay. Now it's not just a what's the word I'm looking for? It's not just a semantic thing, okay? I'm calling it anti-differentiation and not the I word for a very specific reason, okay? So stay with me. Now, watch this, okay? If I were to go back the other way, right, and anti-differentiate. So what I'm trying to do is I'm trying to guess. Now, what function did I come from? Where was I before, and then I differentiated and I got 2x, okay? Now, one plausible answer is x squared, as you can see, because you guys know your rules of differentiation, right? But it's not the only answer, right? Can someone give me another example of an answer? Yeah.
X squared plus 3 times 7 times 9 divided by 2.19.
Simplify that to a number.
How about 1? X squared plus 1. Now, you can see this, right? You can see why, when you go back the other way, it's not so concrete, right? Because x squared and x squared plus 1, I could differentiate either of these, and because you've got your constant term over here, which just disappears when you differentiate, right? You don't know what it is, right? X squared plus 1 could also end up with the derivative of 2x. Does that make sense? Okay. It's not just x squared plus 1. It could be x squared minus, 5, or x squared plus pi, or x squared minus e, whatever. Okay. So what you're getting now is that a derivative is not just one function. Okay. The derivative is one function. It's just a single thing, right? If you have a primitive, it's only got one derivative. Okay. But when you go the other way, you don't just get one, you've got a whole bunch of them, right, that are all related to each other. Okay? So we call them a family. Okay? We call them a family because they're related. Get it? Related? Anyway. They're not just, random other functions. Okay? You can see they have a clear connection. And the connection is these constants. Sorry. I said it backwards. The connection is the x squared. What's different is the constants. Okay. So in order to describe this whole family, right? Just like everyone in a family has this isn't the same for subcontinent people, but generally speaking, everyone in a family has the same surname, right? So think of your x squared as kind of like your surname, right? Everyone's got that in common, but all of your first names are different, right? So if I were to try to describe this family, I'd say, well, the x squared is the important part. And this part over here, your first name, which can be all different, right? I'm going to call it that plus c. Any constant you like, okay? It can be negative, positive, integer, real, transcendental, whatever, okay? So x squared plus c is the whole family of functions that are the primitives of 2x. Does that make sense? Okay, now you can see how algebraically that works, because you know why differentiation, all of these can end up at 2x, okay? But I want you to draw up a set of axes for me, and let's see what that means geometrically. Question.
Can C be an imaginary number? Like
Yep.
not a real number?
Yeah,
And it's
so long as
necessary.
it's constant,
So
because if you differentiate
differentiate
a constant
You can
anything, it'll
differentiate
disappear.
imaginary numbers?
Yep. They are just quantities just like any other in that way, with regard to calculus anyway.
Does C stand
It stands for constant.
for?
So, draw yourself up a set of axes. Question.
No,
Or that, like,
it's
If
specifically
10x was
x
the
squared
derivative,
plus the speed of light.
could the derivative like 5x squared?
Yeah, okay. So we'll get to a few different examples shortly. I just want to look at all of these. Okay, wow, that's a really wonky line, but you guys can do better ones on your paper. What I want you to do is let's draw a few of these together. Let's draw a few together. Okay. So x squared is going to pass through the origin. Okay. But this family, right? It's a whole bunch of functions which look very, very similar. Okay. Now, what's the difference geometrically between all of these? How would you word it?
They're above or below.
Yeah,
each
good.
other.
There's a vertical shift is the way we would say it. Okay. Or they're moved up and down. Okay. So if I've got something like this, say, right? Let's call that 2, right? This would be x squared plus 2. This would be x squared. Let's put one, beneath the axis, something like this. That looks like it's another unit, so maybe that's minus 3. So x squared minus 3. Okay. Now, have a look at all of these, right? What does it mean that these are all equally primitives of this function? okay, it means if you pick a point, any point, let's say, I don't know, x equals 1. Okay, and if you cut through all of the different graphs that we've just drawn, like I need another color. Starts off a bit wonky, but you get it. Okay, what does it mean, right? Well, you guys know that a derivative geometrically it means what? What does it tell us? Gradient. Good. So if you've got these 3 points of intersection, right? This one, this one, this one. Okay. Seeing as all these primitives have the same derivative, right? What that tells you is the gradients at all of those points should be equal. Does that make sense? Okay. To take it one step further, if I were to draw the tangents at all of these points,
It would be parallel.
they would be parallel, right? Okay, all parallel. Does that make sense? Okay. As we go through primitives and later on we get to stuff to do with integration, you've always got to think, number one, about what stuff means algebraically, and number two, what it means geometrically. Okay, that's really, really important. You can't just have letters and numbers, you've got to think about the picture, what it looks like visually. Letters and numbers.